In this talk, I would like to discuss the topics of closure phase and systematic bias in insert time series. With three acquisitions, three interferograms can be formed, and the closure phase is the sum of the three respective phases. For insert time series analysis, we decompose insert phase as the phase difference between two SAR acquisitions. With this decomposition, the closure phase is always zero. Therefore, phase closure is an intrinsic assumption in insert time series analysis. While zero closure phase is true for single-look images, it is generally not true for multi-look observations. It has also been noted in Ansari et al. 2020 that time series analysis with different temporal baseline produces systematically different results. Let's look at these deformation maps produced in Ansari et al. 2020. The only difference between these deformation maps is the imposed maximum temporal baseline. By comparing with persistence gathering interferometry results, Ansari et al. Determined that time series analysis performed with short temporal baseline contains the largest bias. Therefore, their recommendation is to use all possible interferograms when performing insert time series analysis. In this talk, I aim to answer the following question: what links non-zero closure phase and the observed discrepancies among time series? And I'll present a model which will consistently explain both observations. And since non-zero closure phase only occurs in multi-look interferograms, naturally we start by investigating the role of multi-looking. Multi-looking means averaging single-look measurements in a predefined window. Each single-look measurement is drawn from an underlying distribution that is characterized by parameters such as amplitude and phase. If all single-look measurements are homogeneous, then the multi-look phase is the maximum likelihood estimate of the true phase. However, the Earth's surface is naturally heterogeneous, and to make things simple, let's assume that there are two different types of underlying distribution, and in this case, the multi-look phase is a function of phase 1, phase 2, and W, which is a function of the amplitude ratio between these two signals. If we have a homogeneous process, such as deformation, and some heterogeneous process that I denote with X, multi-looking will yield a multi-look phase that is the sum of not only deformation, but also a weighted process X. The weight W is related to the brightness or the amplitudes of the pixels associated with process X. Now let's make the assumption that the weight W is a function of time. Amplitude variations in time can be caused by many processes, such as soil moisture change. For now, let's simply denote W as a function of the temporal baseline. W phi X is therefore the source of the observed bias in time series. With this assumption, we can also form closure phases. Let's decompose a phase into two parts, first deformation and then process X with a weight of W delta T. Delta T is the time span between acquisition 1 and 2. Similarly, we can decompose delta phi 2-3 and delta phi 1-3. The resulting closure phase is not zero because W delta T and W2 delta T are not necessarily the same. Note that the closure phase is only sensitive to process X. And by summing consecutive closure phases, we can extract a weighted phase history of process X. Now let's expand the definition of closure phase. Instead of connecting the loop between 3 acquisitions, we can create a loop of 4 or even more acquisitions. The resulting cumulative closure phase are all proportional to the phase history of process X, but with different weights. Our goal is to obtain a biased temporal baseline curve. Assuming the weights decay with time, the curve may look something like this. With this curve, we can model the amount of bias in each interferogram and hence obtain a bias estimation. Assume the weights become negligible when the temporal baseline reaches m delta t. The cumulative connection m closure phase can therefore give us the first data point. And by subtracting the connection m closure phase from the other closure phases, we can populate the biased temporal baseline curve. And to test our theory, I processed some Sentinel-1 data acquired over the Barstow-Bristol trial of California from February 2017 to January 2021. This is a generally arid area, and it has a few dry salt lakes, which are the blue patches shown in the map on the right. I performed time series analysis using SBAS, and the results also show discrepancies among each other, which is consistent with the findings in Ansari et al. In our case, the bias are particularly obvious in areas surrounding the dry lakes. Now let's look at some closure phase. First, let's look at the triplets. These are consecutive triplets, and by adding them up, we obtain a weighted version of cumulative bias in our time series. The same can be done in other connection level. For example, these are connection 20 closure phase. The sum of these closure phase gives us another weighted version of the bias. If we assume that the weight of the bias at 20 connection is negligible, we can use that to estimate the base bias, and the difference between the two cumulative closure phase can be used to further populate the bias temporal baseline curve. And since we can do that for every pixel, this is the result showing essentially the map version of the bias temporal baseline curve. We can use these maps to identify where bias occur and to estimate the strength of the expected bias as a function of the temporal baseline. In this case, the bias velocities are negligible when the average temporal baseline reaches 45 days. And with that, we can compute and estimate bias in each of the time series. And the bottom figures are the estimated bias. And after removing them, the corrected velocity maps are now consistent with each other. We can also correct time series. Let's take a close look at one pixel near a dry lake bed that is marked by the black star. With our model, we can correctly predict the amount of bias and remove them from the original time series. Although I have been calling it bias in the context of deformation modeling, these are real physical signals reflecting changes of surface properties. Here, I plotted the extracted bias time series in black and the cumulative precipitation in this region in gray. The correlation between the precipitation and the bias time series strongly suggests that the bias may reflect soil moisture variations after precipitation events. And here are my summaries. First, heterogeneous processes within a multi-look window that induce both amplitude and phase change are the root cause for both non-zero closure phase and bias in INSAR time series. We have shown that by using cumulative sequential closure phase, we can easily identify areas that may subject to bias. And depending on the decay rate of the bias, a small baseline analysis may not have significant bias in some cases, while in other cases, a full bandwidth analysis may still contain bias. And lastly, the bias are real signals that may reflect real properties. And that is all. Thank you.